In Queensland, as in many places around the world, there is an increasingly pressing need to protect ourselves from severe weather events such as thunderstorms and cyclones.
So at the November 27th hailstorm, we had well and truly in excess of 800 calls for assistance just because of broken windows. It seems crazy that a bit of hail can break a window so easily, so we well and truly need better standards for our windows.
This situation has given rise to the design of more advanced technologies, for which the assurance of quality and performance in extreme conditions requires a sophisticated approach to the development and manufacturing processes. Our team from the University of Queensland is working alongside Centaur, a multi-award-winning company based in Brisbane, to design and build a compressed air cannon that will be used to test the impact resistance of Centaur's door and screen systems.
This project is to build Chicken Cannon number 2, a bigger and better version of one we constructed about 8 years ago in order to test doors which we were trying to sell into southeastern USA, Florida in particular, where they have stringent regulations about resistance to airborne debris impact during storm events. However, the latest Australian standards will require us to take that maximum speed from 24.5 metres per second up to a potential 50 metres a second. So we're looking at a complete redesign, not only in performance, but along with many other enhancements which will lift it from a rapidly constructed piece of equipment to something which is hopefully very impressive.
Pneumatic air cannons have been constructed for a variety of purposes. The concept has reportedly been applied by the FAA and NASA with great effect to test the strength of cockpit windshields and jet engines. The test methods involve firing chicken carcasses at high velocity to simulate bird strike and assess the resistance of specimens to such an event. Recreationally, the use of pneumatic cannons are widespread over a range of scales. The world record for pumpkin chucking was achieved using such a device, with a range of almost 1.7 kilometres.
Previously, it was prescribed by the ASTM international standards that exterior windows and doors must be able to withstand an impact by a 4 kg projectile travelling at 25 metres per second. However, imminent changes to the standards will see this velocity requirement doubled to 50 metres per second. To achieve this, our design is to comprise velocity measurement and calibration capabilities, which will evaluate the trajectory in terms of the model conditions and obtain an initial pressure requirement for a nominal impact velocity at a required range of 1.5 times the projectile length. The client has also requested a more accurate aiming system through a height range from 800 to 3800 millimetres above ground level. To accomplish this, we will deliver a laser aiming device with an automatic calibration system. Our team has resolved to operate in an open network structure, with each member designated the management and coordination of a key aspect of the overall project. Similarly, the technical design task has been divided into a number of components, with the primary responsibility of each being assigned to one member of our team. Our challenge is the integration of components to ensure optimal functionality of the design as a whole.
For this project, my tasks include the design of a tank and air release valve. This part of the system must be able to release a sufficient volume of air to launch the 4 kg projectile at the Australian standard speed of 50 metres per second, whilst using the air available at Centaur of 8 bar. Another important aspect of this part of the system is safety. The stored energy within the pressure vessel poses a high safety risk, which will need to be effectively managed to prevent harm to users and equipment. In addition to this, I'm in charge of the integration of the FMEA between subsystems and dealing with the supplies and acquisitions of necessary resources.
My contribution to the project will be to design the barrel of the cannon and the sabot. The sizing of the barrel is crucial in enabling the projectile to reach its target velocity. It will require an appropriate caliber to generate sufficient propulsive force and length enough to allow time for acceleration. The design of the barrel must integrate with the valve mechanism at one end and the velocity measurement equipment at the muzzle. For our purpose, the sabot must accommodate the firing of a rectangular projectile from a round barrel, by maintaining its alignment and creating a dynamic seal to contain the compressed air. It is therefore a key determinant of the cannon's efficiency. Design of the sabot must also manage interference with ballistics and observe the requirements of the ASTM international standards. In addition to my technical design task, it is my job to coordinate the compilation and editing of all reports and presentations. It is also my responsibility to maintain the Gantt chart, to take meeting minutes, and to oversee document management.
My task is to design the aiming and mounting systems for the cannon. The relevant standards specify that the centre of the projectile must impact the target within a 65mm radius of the intended impact point. Each tested window or door must be impacted at a number of specified points, spanning the height and breadth of the pane, with the incident angle of the projectile less than 5 degrees from normal to the target. Therefore, our system requires coarse and fine vertical and lateral adjustment capabilities to accurately aim the projectile with a high degree of repeatability. In order to aim the cannon for each test, a laser beam will be projected from the barrel down the range and onto the target. Furthermore, I am in charge of the project budget, and as team director, I maintain efficient and effective communication within the team and monitor performance and work distribution.
My role for this project will be the Technical Design Director. This will involve overseeing the technical design and coordination between the various subcomponents and maintaining compatibility between them. My design tasks in this project involve designing the subframe assembly, which will serve to not only support the cannon, but to absorb the recoil impact from the projectile, decreasing the movement, hence increasing its safety and accuracy required by the ASTM standards. I'll also be overseeing the design of the firing wall along with the mounting that will help absorb the projectile impact. This is critical as the ASTM standards require the test specimen to be anchored in an identical fashion to how it would be mounted in practice. It is also necessary to impede any backwards motion of the firing wall as to maximise the impact force. In addition to these tasks, I'll also be working to create 3D CAD models and mechanical drawings of our design. These will help to support our CFD analysis to be carried out later this year. Additionally, I'll also be managing the key performance indicators for this project over the course of the year.
My tasks for this project involve designing and calibrating a speed measurement system and potentially developing a control interface for the cannon. The standards relevant to speed acquisition are especially important. These state that the speed measurement must be taken once the acceleration caused by propulsion is equal to 0. This means that the speed measurement of the timber projectile must be taken once the projectile has completely exited the barrel. The measured speed must be also within 1% of the specified speed for a projectile launch of over 23 meters per second, and so a finely calibrated fast response system is necessary. We will be using 2 photoelectric sensors for this. My role as Systems Modelling Director is to coordinate the theoretical models obtained by each team member and oversee the development of these into a complete theoretical system. I'm also in charge of maintaining team progress reports for Centaur.
The preliminary design stage has seen the assembly of key ideas and information based on prior art research and the review of relevant literature. After establishing an initial design, the use of modelling software will enable the refinement of our model and an analysis of its anticipated performance. Our aim is then to build a functioning prototype which will allow for the evaluation of our virtual model and, if necessary, accept minor modifications. With our preliminary design nearing completion, we anticipate a review of our intermediate design by the 3rd of August, with the finalisation of our physical design and component specifications by early September. Pending negotiations with Centaur, an immediate build would allow us to include prototype revisions in the final design report, which is to be delivered by the 31st of October.
Our team is working hard to develop a refined and effective technical design and hopes to deliver a fully operative compressed air cannon with functionality tailored to Centaur's requirements by the end of the year.